Units. To make measurements, we have to have some units. And this is an example of why units are very important. Back in 1999, NASA lost the $125 million Mars Climate Orbiter. They sent it up there, goes into orbit. The orbit was wrong. The orbit, it descended too low, and so it crashed, burned up. Actually, it didn't crash, it burned up probably before it got to the surface of the Martian planet, the Mars planet. And so, of course, there was a big investigation. Chairman of the committee concluded the root cause of the loss of the spacecraft was a failed translation of English units into metric units. One group of engineers was using inches, one was using centimeters. Dang. Inches, centimeters. Units matter. Okay? Sometimes students complain, well, you're so picky. You know, it was almost right, it was close. Well, you know, I'd love to be able to give that to you, but close only counts in horseshoes and hand grenades, right? It doesn't count when you're calculating things. Close isn't good enough. Close doesn't count in email addresses, right? You get one letter wrong in that email address and it's not going anywhere. You're emailing your boss that you're not going to be able to come in, and you get one letter wrong. He never gets the message. You get in big trouble. Details matter. There are places where details are not as important, and one of the tricks is learning when they're super important and when they're not so important. But in chemistry, details matter a lot. So units. Units are standard quantities used to specify measurements. And there are two main systems of units that are used in the world. The metric system, which most of the world uses, and the English system, which here in the United States we have clung to like a life preserver or something. It's more like a lead weight pulling us down. So the English system is things like inches and yards and gallons. And the metric system is centimeters and grams and liters. So scientists use the International System of Units. It's called the SI system, based on the French. Scientists got together and decided on the units and how the units would be defined. And this is the SI system. So how is the SI system different from the metric system? It's only different in the base units. And so I really don't care if you know what the base units in the SI system are. I care about, do you know what a gram is, and can you convert it to a kilogram? So for my purposes, the metric system and the SI system are the same. These are the base units in the SI system. For length, we use meters. The abbreviation for that is a lowercase m. Mass is a kilogram. Symbol is lowercase k, lowercase g. In chemistry, we use grams more frequently because it's a smaller, more useful unit. Time is measured in seconds. That's okay. That's the same as our seconds. Temperature, the base unit for the SI system is the Kelvin, and that's symbolized by a capital K, and we'll learn about that in a bit. The amount of substance is a mole. We'll also learn about that. That's abbreviated MOL. And then electric current and luminous intensity are things that we're not going to run into in chemistry, but it's the ampere and the candela. So a meter. It is very helpful to have a basic understanding of how big a meter is. A meter is roughly the same size as a yard. So here we have a meter stick. This is not a yardstick. This is a meter stick. That's how big a meter is. There's the meter side. If you look on the inch side, it's a little over 39 inches. So it's just a little bit bigger. But having that basic idea that a yard and a meter are about the same length will help you to know that if someone said they were 7 meters tall, that would be ridiculous, right? Because that'd be like 21 feet tall. Nobody's been that tall. The definition of these units is very precise. I've put them up here, but you do not need to remember that. The kilogram is the SI base unit of mass. A kilogram is 2 pounds, 3 ounces. So a kilogram is about 2 pounds. So that's a good thing to understand. A very common unit of mass, and the one we use most in chemistry, is the gram. A gram is 1/1000th of a kilogram. And so a useful thing for gram is that a nickel, 5 cents, weighs about 5 grams. So a nickel, 5 grams, 5 cents. Yes?
The only one you say 1 pig is 2 pounds, 3 ounces.
Mm-hmm.
I'm the air technician, and I do injections all the time.
Mm-hmm.
And we do everything by like 2.2.
Right.
Pounds, like if I go weighs 2
Yes.
pounds, I'm dosing
2.2. So 2.2 means 2 pounds and 2/10ths of a pound.
Okay.
2 pounds, 3 ounces is 2 pounds and 3/16ths of a pound. Because ounces are 16 ounces in a pound.
So if we're converting in lab for here, are we going to do the 2 pounds, 3 ounces?
No.
Okay.
I'm not sure why they put it like that. Let's make it better. Or 2.2 pounds. Yeah, good question. And this kind of points out a messy part of the English system. You know, if you're talking about 2.4 feet, that's not 2 feet and 4 inches. Because the divisions aren't tenths, they're twelfths. And with pounds, it's 16ths. And it's just all these seemingly random numbers. There are historical reasons why all those units are the way they are. I think they're silly, right? And they're hard to remember. And so learning the metric system is challenging sometimes for students. Once you get it, though, it's really much easier because everything is based on tens. And so there's not any crazy things to remember. Quick word about weight versus mass. Weight is the measure of gravitational pull on matter. How hard is the Earth pulling on you? Your weight changes, and it can actually change very slightly based on where you are on the Earth. Those differences are usually not very important. But if you were to go to the moon, your weight would change significantly because the moon is much smaller and its gravitational pull is less. Does that mean that you're like skinnier on the moon? No, it's the gravitational pull. So mass measures amount of stuff. The mass doesn't change if you're in outer space or if you're on a bigger planet, a smaller planet, but the weight does. So we use the word mass, but sometimes we'll throw in the word weight, and we're not going to worry about that, but I just want you to be aware that there is a difference between weight and mass. Time is measured in seconds, and there's a very specific definition of that. We all know what time is and what seconds are. Kelvin is the SI unit of temperature. Temperature measures the thermal kinetic energy of the atoms and molecules in matter. And temperature will also determine the direction of thermal energy transfer. When thermal energy moves from one substance to another, we call that heat. So we know from life experience that thermal energy is transferred from hot objects to cold objects. If you put an ice cube in a cup of hot coffee, the ice cube is going to get warmer and melt, and the coffee is going to cool down. Heat goes from the coffee into the ice cube. It doesn't go the other way, where the coffee gets hotter and the ice cube gets colder. That's ridiculous, right? So heat always flows from the hot thing to the cold thing. So temperature tells us which direction heat will flow. So there are 3 temperature scales. In the United States, we're familiar with the Fahrenheit temperature scale. And on this scale, water freezes at 32 degrees Fahrenheit and it boils at 212 degrees Fahrenheit. Again, just seemingly random numbers. There are historical reasons for that, but we're not going to get into that. So that is considered an English system unit of temperature. So metric would be Celsius and kelvins. So on the Celsius scale, it was set up so that water freezes at 0 and boils at 100. And so there are 100 Celsius degrees between water boiling and water freezing and 180 Fahrenheit degrees. So the size of the degree is different and the 0 is different. Here 0 is at water freezing, here 0 is below that. On the Kelvin scale, the Kelvin scale is based on the concept of absolute 0. So absolute 0 is the coldest theoretical temperature. Temperature is a measure of the kinetic energy of the individual particles moving around. So 0 kinetic energy means the atoms are not moving at all. That's like all of the students, petrified. Not scared, literally petrified. Your heart's not beating, nothing is moving. That would be absolute 0. So that's a theoretical temperature. And then if we apply this scale, they're keeping the same number of divisions between water freezing and water boiling. And so the Kelvin scale is just offset in 0 from the Celsius scale. You can never have a negative temperature on the Kelvin scale, and that's why it's really useful. You can have negatives on the Celsius and the Fahrenheit. So to convert temperature scales, we need to use equations. And so here they are. We've got the degrees Celsius equals the Fahrenheit temperature minus 32, that quantity divided by 1.8. To convert from Celsius to Kelvin, you take the Celsius temperature and you add 273.15. Those are equations that you should learn and memorize. Okay. So let's do an example. Gallium is a solid metal at room temperature, but will melt to a liquid in your hand. Pretty crazy. The melting point of gallium is 85.6 degrees Fahrenheit. What is this temperature on the Celsius scale and on the Kelvin scale? So we have 85.6 degrees Fahrenheit. We want the Celsius temperature. Well, we have that equation. The temperature in Celsius is the temperature in Fahrenheit minus 32 divided by 1.8. The minus 32 takes care of the difference in 0, and dividing by 1.8 takes care of the difference in the size of the units. So we put the number in here, 85.6 minus 32, and divide all of that by 1.8. Forgot my calculator, but I have my phone. Come on. So 85.6 minus 32 equals, and then divide by 1.8, 29, and round that to 29.8. Always a good idea to bring your calculator. There will be days when we don't use them, but bring them anyway. And do it on your calculator. I screw up fairly regularly, and it's always fun to tell the teacher, hey, you did it wrong. Also, sometimes we miscommunicate with our calculators, and if you're doing the problem along with me, then we can become aware of those before we lose points on an exam. Any questions about that conversion? It also asks for the Kelvin temperature. So we need to take this Celsius temperature, convert to Kelvin. Kelvin equals degrees Celsius plus 273.15. So we take our 29.8 plus 273.15. and we get 302.9 Kelvin. The Kelvin unit is just a K, it doesn't have a degree. Celsius and Fahrenheit are degrees. These are just, Kelvin is Kelvin. Any questions?